Greetings everyone, I am Sujit Kani here to present Project Insight, an initiative to run an ML model for stereo depth estimation by FPGA hardware acceleration on a PolarFire SoC Icicle kit alongside my collaborators Sanjit Krishna S. Under the mentorship of Dr. Gracia from Department of ECE, Kumaraguru College of Technology. Our project aims to advance embedded systems and ML application by hardware acceleration. So now I'll show a quick overview through our project, and Sanjit will later explain about the FPGA and the machine learning implementation of the project. So initially we got the kits by the first week of October 2024, and we initially installed all softwares and IDEs and the tools required alongside using the board, and we went through the quick start card which allowed us to get in good hands with the kit. And then we initially ran a few bare metal programming examples on the PolarFire SoC Icicle kit to work with the RISC-V course. And then we learned the design flow for the same. And also alongside we began learning HDL and Verilog design for simple circuits using the Libro SoC software. And we ran through two iterations of interfacing cameras for stereo depth estimation, and this was the first unboxing of the PolarFire SoC Icicle kit and the various software tools required. We used Libro SoC Design Suite, Soft Console IDE, and MSS Configurator on platform of both Windows and Linux. And our first run was to go through a quick start card and invoke a pre-built Linux and invoke the pre-built Linux kernel to launch a web server, which was built in. And this was our first boot. Here we can see the microchip logo alongside with the pre-built Linux kernel booting up without any errors. And this was the first web server which was pre-built along with the Icicle kit. It shows a sensor analysis of current and voltage at various points in the Icicle kit and the silver license. So after this, we went to software setup where we set up the Libro SoC, which required a silver license, and we went through user guide in the microchip website and registered silver license for two different nodes. And then we ran few examples of bare metal programming through various GitHub repositories where we got a few support. And this was our MSS configurator, which we set initially to run a bare metal programming of running on the RISC-V CPU. This was the soft console, which was basically an NetBeans Eclipse IDE, where we used C++ programming to run a basic Hello World program. Here we can see the C++ indexer or indexing the various sources, and the MPFS program on Renode is being started for debug. This was a first build without any errors, and the output. Here we can see each core is invoked for a Hello World program which prints Hello World from each course U54 core 1, 2, 3 through 4. This was the PolarFire SoC's initial MSS configurations set up for the FPGA fabric, which we left undisturbed at the starting. And then coming to the Libro SoC. Libro SoC, where we designed the digital logic for basic gates, basic digital circuits, and we experimented with that to get along with the FPGA part. And then camera interfacing. So here the project is of two phases where we focused on camera interfacing at a point of time and then going along with the ML acceleration. So camera interfacing was actually tiresome. Initially we tried to implement a 767 camera module to the PolarFire SoC Icicle kit using the Raspberry Pi GPIO pins. And then we tried to convert the proof of concept from Python in OpenC v2 C++ for implementation, and this was our first setup. Here you can see we got the OV767 camera module, which is interfaced along with the Raspberry Pi pins, which was not a proper way to go. So we went through another iteration of capturing the frames on a separate device and then transferring the frames to the board in real time and networking. Here this was a major part where we interfaced two separate webcams to the Icicle kit and installed a few packages for file management in Linux systems. We tried SD card booting, capturing and transferring video data by setting up a HTTP server, running on troubleshooting, and then we went through ML models for face detection. And the outcomes. Here at this stage, we successfully organized both webcams with the interface, and the board was able to recognize the cameras. But unfortunately, we were not able to verify the output from both cams because we needed troubleshooting and we had to install few packages for file management. As it is a kernel with very limited resources, so here we can see we have set up gigabit Ethernet and various tools we have used. We tried booting using SD card by booting to a separate layer of another Linux distribution for RISC-V, and then we installed various tools like V4L utilities for video and image files for multimedia purpose and BusyBox. So we already had a Octo BSP running on the board itself after SD card boot failed. And then we made two cameras record on a Windows PC simultaneously and transfer the recorded video to the kit by hosting a HTTP server. So this was our first run where we installed various packages. As you can see here, we got the V4L utilities installed with few drivers and QVID cap and other V4L CTL and library V4L. And this was our first run where we transferred both videos recorded from camera simultaneously on a Windows device to the Icicle kit through HTTP server. But we had latency. We had a greater latency while transferring these files. It took around 16. This was for a greater speed, around 16 Mbps. But in real time, we cannot tell it is a reliable way to transfer files. So we moved on to other methods by hosting a HTTP server and transferring frames simultaneously at 1 frame per second. We tried this. So this was our Python setting in a separate Windows PC where we were running HTTP server which captured the video frames stored in a separate folder and then transferred it to the Ubuntu kernel running in the Polarfire Icicle kit. And we can see here we wrote a separate bash script on the Icicle kit to receive the frames simultaneously and store it in two different folders. So this was a configuration. You can see here we got a fetch frames.sh, the bash file, and two separate folders. So here in Python we can see the cameras are connected and the HTTP server is being hosted on 192.168.2.2, and then we moved on to Ethernet socket method. So HTTPS method was not much reliable because sometimes we lost many frames. We have captured for around 5 minutes and at the end we got only 2 to 3 frames captured, which is at the last moment of file transfer. So we moved on to another reliable method for other Ethernet port. We had 2 gigabit Ethernet ports. We went to Ethernet socket method where we use the other Ethernet port to connect to a separate and dedicated port for file transfer. The same thing which we ran using the socket module in Python, you can see here. Here we use the time module to transfer each files frame by frame per second. And this was first run for capturing the frames from the PC. Here you can see that the frames are being captured simultaneously from the PC and transferred to the Icicle kit for a rate of 1 frame per second. So this was our final iteration of transferring frame by frame from a separate Windows machine where it supports two webcam. You can see this setup. Here we got our webcams which was capturing the frames simultaneously from the machine and transferring it to the Icicle kit to serial ports. I mean the Ethernet socket method. You can see each frame is captured. This was captured for around 2 minutes and we got around 120 frames at almost at the rate of 120 frames per second, which is almost far enough for giving real time input to our machine learning model, which is being run in the FPGA fabric. Now my friend Sanjit will continue on with the FPGA fabric.
Um, Good day, everyone. I'm going to give you a very quick overview on using the PolarFire SoC iCycle kit for stereo depth estimation by leveraging FPGA and machine learning on the kit itself. So on your right, we have our Libro SOC toolkit, and then on your left, we have our notes that we're going to refer, and we're going to explain how our project works. So our objective is to mainly run a machine learning model on the FPGA fabric that can process stereo image pairs for estimating depth while using low power consumption and having it reasonably real-time processing. So, core system designs, we can tell here there are different types of core system designs. So, we'll go a quick brief overview. So, system designs include a RISC-V CPU cores, DDR4 memory, vector block accelerator that we'll come back to later, AXI interconnects, uh, uh, and a bunch of hardware connections that are also necessary for the usage of uh, the FPGA accelerator. But what is this FPGA accelerator? So, from in our project, we have utilized something called a vector block CNN accelerator. The vector block CNN accelerator is nothing but here, vector block CNN accelerator. So this vector block CNN accelerator uh, runs a .vnxs file format machine learning model that can be converted using another tool available on Linux. So once we convert your normal, in this case, open neural network source format machine learning models to .vnxs, we can upload it to core vector block and that will automatically map it to the FPGA fabric. To synchronize all of this, we have our mic, we have our RISC-V CPU to help us synchronize all of this, which has also been fed into, which also has been powered by its own proprietary clock signals, controlled by this oscillatory control clock circuit. So all of this connects into the DDR4 memory buffer for in order for us to use and store memory and data from all our images for pre-processing and post-processing purposes. This gives a general overview on what the uh, FPGA for depth estimation project does. Thank you.